A teaspoon of star stuff can weigh more than a mountain. That's a real thing. It's not a story. The cosmos is full of events and objects that seem to break every rule. They seem impossible, but they're governed by real laws, physics. So we're going to look at 25 cosmic phenomena. They appear utterly impossible. And by the end, you'll understand the principles, the scientific principles. They're elegant, often bizarre, and they make these things not just possible. They make them inevitable. How can empty space boil with particles that don't exist? What force is stretching our universe apart, stretching it faster and faster? The answers are in known physics. They're waiting there to reveal a reality far stranger than fiction. So what part of our universe still feels like magic to you? The collapse starts inside a dying star's core. Its own gravity, no longer balanced by fusion, turns inward, catastrophically. In that final supernova, the outer layers blast away. What's left, the heart, gets crushed down, and what comes out of that violence is something so dense it doesn't make sense in our world: a neutron star. You could take our sun and squeeze it into a sphere the size of a city. That's what you'd have, matter pushed to a breaking point. Inside, the pressure overcomes everything that holds an atom together. Electrons get driven into protons, they merge, they become neutrons, so you get this vast, city-sized atomic nucleus, a sea of subatomic particles packed shoulder to shoulder. Almost no space. A sugar cube of that material would weigh as much as every person on Earth. That density, it's not magic, it's a precise, violent balance. Two titanic forces, on one side gravity, Einstein's gravity from general relativity pulling with unimaginable strength, on the other, a quantum pushback. Degeneracy pressure, it's a fundamental rule. Particles like neutrons refuse to be squeezed into the same state. That resistance is the only thing stopping gravity from crushing the star into nothing. The balance is perfect. It creates a stable but utterly alien form of matter, and we know they're real because we see their effects. Some neutron stars spin. Dizzying speeds, beaming radiation like cosmic lighthouses. Those are pulsars, first observed by Jocelyn Bell Burnell. Their rhythmic pulses are so precise they rival atomic clocks. A direct signal from the heart of this extreme physics. Neutron stars are natural laboratories. They test our understanding of matter under conditions we could never recreate. They show us the universe allows realities that seem impossible. And if crushing a star into a city seems extreme, consider what happens when gravity wins that final battle. When the neutron star's quantum defiance fails, the collapse doesn't stop. It continues into a realm where the known laws of physics are stretched to the limit. That final defiance fails when the core is too heavy. The neutron star's quantum pressure gives way. Gravity wins. It wins completely, and that's the birth of a black hole. A region of space where the pull is so intense nothing can escape, not even light. It creates a boundary, a point of no return, the event horizon. Cross that line, and the path back to the rest of the universe closes forever. To us, it looks like perfect darkness, a hole in the fabric of reality. But this isn't a monster. It's a direct mathematical prediction from Einstein's theory of general relativity. When a massive object collapses beyond a certain critical radius, space-time curves so severely it folds in on itself. At the very center is a singularity. A point where our current laws of physics, our understanding of matter and gravity just break down. The equations point to it, but they can't describe it. It's a frontier, but the black hole itself, the region of space it commands, is real. It's governed by known rules, and stranger still, black holes aren't entirely black. The work of Stephen Hawking revealed a blend of gravity and quantum mechanics. He showed that right at the edge of the event horizon, pairs of virtual particles, that constant quantum fizz of the universe, can be pulled apart. One falls in, the other escapes. To an outside observer, that stream of escaping particles looks like a faint glow. Hawking radiation. It means black holes can, over incomprehensible stretches of time, slowly evaporate. They have a temperature, they obey thermodynamics. That subtle glow is one of the deepest clues we have for how to finally unite the worlds of the very large and the very small. And we know they're out there. We've seen their shadow. The Event Horizon Telescope collaboration produced an image, not of the black hole itself, but of its silhouette against the glowing matter swirling around it. That iconic image of the supermassive black hole in galaxy M87, it's a direct validation. It matches what Einstein's equations told us to expect over a century ago. Black holes teach us that the universe's rulebook allows for outcomes that seem paradoxical. A place where light is trapped, yet it also slowly leaks away. A place where time, as we know it, stops, yet within the framework of physics it all holds together. And from these realms of ultimate darkness we find a counterpoint. In the universe's most brilliant explosions, that faint Hawking radiation is a cosmic whisper, but the universe also screams, in a flash of light so brilliant it defies comprehension. Gamma-ray bursts. For a few seconds, they outshine every star in their entire galaxy. They release more energy than our sun will across its entire 10 billion-year life. All in a moment, it seems like a universe-shattering event, an impossible violence, yet it is born from known, if extreme, physics. These bursts come from the death throes of the most massive stars, or from the final dance of two neutron stars merging. When such a star collapses, it doesn't just go quietly. It can launch jets of material, not just any jets. These are beams of plasma traveling at almost the speed of light. They are focused like cosmic blowtorches, and when these ultra-relativistic jets slam into the surrounding gas, they create shock waves. Inside those shocks, particles are accelerated to fantastic energies. They collide, and in that chaos they produce the highest energy light we know, gamma rays. This is the physics of special relativity and magnetohydrodynamics in action. It is a titanic conversion of raw kinetic energy, the energy of motion, into a beacon of radiation visible across the cosmos. We've seen them, thanks to satellites like SWIFT, developed by scientists like Neil Gehrels. We catch these fleeting flashes. We trace them back to galaxies billions of light years away. We've linked the longer bursts to supernova, the explosive deaths of giant stars, and we've connected the shorter, sharper bursts to the mergers of neutron stars. That merger event is more than just a flash. It is a cosmic forge. In the incredible heat and pressure of that collision, atoms are smashed together. They create the heaviest elements in the universe, gold, platinum. These cataclysms happening across space and time are literally seeding galaxies with the very materials that will one day form rocky planets and perhaps life. It is a profound connection. The most violent explosions in creation are responsible for the metal in a wedding ring. They obey the strict conservation of energy and momentum. The math holds even here, so while a gamma-ray burst would be catastrophic for any nearby world, it is not magic. It is physics operating at its most ferocious volume. And it reminds us that from the darkest collapses and the brightest explosions, the universe is constantly recycling, creating, and scattering the seeds for what comes next. From that unimaginable energy, we find a shift to a phenomenon defined not by brilliance, but by profound and unsettling silence. That brilliant flash fades. You're left with the deepest quiet there is, the vacuum of space. It's not just an absence of air, it's an absence of everything, a perfect, empty nothing. Or that's how it seems, but according to quantum field theory, which is our most accurate picture of reality, that emptiness is a lie. the vacuum isn't empty. It's alive. It's a seething, bubbling foam of potential. At scales too tiny to see, particles and their anti-particle partners are constantly flickering into existence. They borrow energy from the universe itself. They exist for a moment, unimaginably brief, and then annihilate each other. They return the energy. These are virtual particles. This ceaseless dance is quantum vacuum fluctuation. It feels like getting something from nothing, like a violation of a sacred rule, the conservation of energy. But it isn't. The genius of Werner Heisenberg's uncertainty principle opens a tiny loophole. For an extremely short time, the amount of energy in a region of space can be uncertain. These particle pairs exploit that. They borrow energy, but they have to repay it almost instantly. The universe allows a fleeting debt so long as it's settled immediately. And this isn't just a mathematical curiosity. We can see its effects. Take two plain, uncharged metal plates, place them incredibly close together in a perfect vacuum. They will be pulled toward each other. That's the Casimir effect, named for the physicist Hendrik Casimir. What's pushing them? Outside the plates, the full spectrum of virtual particles can flicker into being. In the narrow gap between them, only certain wavelengths fit, so the pressure from the particles outside becomes greater than the pressure from within the gap. The result is a gentle, measurable force, a force born from the activity of particles that technically do not exist. This quantum froth isn't confined to tiny lab experiments. It's woven into the history of everything. Cosmologists believe these very fluctuations, stretched to cosmic scales during the universe's rapid initial expansion, a period called inflation, became the seeds for all structure. They were the faintest of wrinkles in the fabric of spacetime. Over billions of years, gravity amplified those quantum whispers. They grew into the vast cosmic web of galaxies and clusters we see now. Our entire observable universe, with its billions of galaxies, may have its origin in the random, frantic buzz of the quantum vacuum. So the next time you look up at a dark, quiet night sky, remember you're not looking at nothing. You're looking at a quantum ocean in constant creative turmoil, a foundational hum that, against all intuition, built the world. And if the vacuum itself is this restless, what does it mean for the very stage it plays upon? What happens when that stage, spacetime itself, isn't just a backdrop but a dynamic, rippling entity? That quantum ocean has a shape, a geometry dictated by what's inside it. And that geometry can act like a lens. Light traveling across the cosmos, it doesn't always go straight. It follows the curves. When it passes near something massive, a galaxy or a cluster, its path bends. That's gravitational lensing. It feels like a trick, a cosmic illusion. A single distant galaxy can appear to us as multiple images, distorted, stretched into arcs, smears of light. Sometimes, if the alignment is perfect, it forms a complete ring of light around the mass in front, an Einstein ring. It looks like a halo forged by the universe. This isn't magic, it's a direct consequence, a beautiful one from Einstein's theory of general relativity. Mass doesn't just pull on objects, it curves the stage they move on. The fabric of spacetime, light, always taking the shortest path, just follows that curved geometry. Think of a marble on a stretched rubber sheet. You put a heavy weight on the sheet. The marble's path curves around the dent. The light is the marble, the massive galaxy is the weight, the curved sheet is spacetime. Astronomers with telescopes like Hubble, they don't just see these arcs as curiosities. They use them as tools. This natural telescope can magnify galaxies so distant, their light has been traveling for over 13 billion years. It lets us look further back in time than we ever could alone. But the lensing effect is often stronger than it should be, stronger than the visible mass of the foreground galaxy can account for. That discrepancy is one of our strongest pieces of evidence. Evidence for dark matter, the invisible stuff, the mysterious stuff that makes up most of the mass in the universe, its gravity is curving the light, revealing its presence through the distortion. So gravitational lensing does more than warp images. It confirms a truth from relativity. Mass tells spacetime how to curve, and that curvature tells light how to move. Even the fastest thing in the cosmos has to obey the geometry of the stage it travels on. If mass can bend the path of light that dramatically, it raises another question. What does that same curvature do to time? The geometry of space bends and time stretches, it compresses. You can take two clocks perfectly synchronized, put one on a rocket moving at a significant fraction of light speed, leave the other on Earth. When the rocket comes back, the clocks disagree. The traveling clock shows less time has passed. That's time dilation. It's not a flaw in the clocks, it's a feature of reality. Einstein's theories predicted it. Our everyday assumption that time ticks at the same universal rate for everyone is an illusion. It's a local convenience, and it breaks down when you move fast or stand in a powerful gravitational field. The key is the speed of light. Light in a vacuum always travels at the same speed. For every observer, no matter how fast they're moving, this cosmic speed limit is absolute. To keep it constant, something else has to give. That something is time. And space, they become flexible. For an object moving at high velocity, time relative to a stationary observer slows down. That's special relativity. But gravity does it too, the curvature of space-time. The stronger the gravity, the slower time passes. That's general relativity. A clock at sea level ticks slower than a clock on a mountaintop. Where Earth's pull is a tiny bit weaker, we have to account for this to make modern life work. The atomic clocks on GPS satellites orbit in a weaker gravitational field, and they move at high speed. Both effects change their tick rate compared to clocks on the ground. If engineers didn't correct for this, GPS positions would drift by kilometers every day. The technology in your phone relies on that understanding. Time's flexibility. We see this in nature's own laboratories. In particle accelerators, unstable particles called muons are created. At rest, they decay in microseconds, but when accelerated to near light speed, their internal clocks slow down. From our perspective, they live long enough to travel much further than they should. A direct observation of time dilation in action. This transforms time from a rigid backdrop into a dynamic player, woven inseparably with the three dimensions of space. It reveals a universe where your experience of now and my experience of now can be genuinely different, yet both are equally valid. So if time itself is this malleable, what other cosmic rules might be bent? What happens when we look out and see something apparently moving faster than the ultimate speed limit? A jet of plasma looks like it's moving faster than light. We see it through telescopes. A bright knot of material shot out from a galaxy's core seems to cross huge distances in just a few years. That would break the universe's law. But it doesn't. It's superluminal motion. It's an illusion. The trick is geometry and the fixed speed of light. Think of a fire truck coming toward you at night, siren on. The sound waves get compressed so the pitch rises. Now swap sound for light. Swap the truck for a jet of matter, shot from a black hole at over 99% light speed. And it's pointed almost right at us. The jet is chasing its own light. As it moves, it makes new light, but that new light has a shorter trip to reach us than the light emitted just before. From where we are, the time between those light signals gets squeezed. It makes the jet look like it's sliding sideways across the sky at a speed that, if you just did the simple math, would be many times light speed. That's a relativistic effect. It comes from the jet's extreme velocity and its lucky alignment with our view. Astronomers see this with quasars, with active galaxies. They use special relativity to work it out. They factor in the angle, the real speed, and it always shows the jet's matter is still below light speed. It follows Einstein's rule: nothing with mass can hit that barrier, so this impossible speed isn't a broken law. It's a sign of how strange perspective gets in a relativistic universe. Our raw observations can deceive us. We have to interpret them through physics. The universe isn't breaking its rules. It's showing how those rules, when you really see them, create something far more interesting than a simple limit. They allow for apparent miracles that turn out to be elegant tricks, and if one jet can create such a convincing illusion of impossible speed, it makes you wonder. What other vast motions are hidden in plain sight, operating on a scale that dwarfs even the most energetic black hole? That speed is an illusion, it's just perspective. But there's a real expansion, a deeper one woven into everything. It happened at the very beginning, in a fraction of a second so tiny it has no name. The universe changed. It went through something so violent it doesn't make sense to our intuition. It expanded from smaller than a proton to larger than everything we can see now. That's cosmic inflation. It sounds like a fantasy, an impossible growth spurt, but it's a theory. It's grounded in physics. It was proposed to solve mysteries. Before inflation, the universe was hot and dense, a quantum soup, but it had puzzles. The cosmos is remarkably uniform. Every direction we look, it's the same. Distant regions on opposite sides of the sky have the same temperature, even though there hasn't been enough time since the Big Bang for light to travel between them. For heat to even things out, it's like two people in separate, soundproof rooms humming the same note at the same time without ever communicating. How could that happen? Inflation gives an answer. Physicists like Alan Guth worked on this. The theory says in that first sliver of time, the universe was dominated by a unique state. A hypothetical field, the inflaton field, it had a peculiar property. It generated a powerful form of repulsive gravity. Think of it as anti-gravity. A pressure that pushed space itself apart, not just quickly, at an ever-accelerating exponential rate. This wasn't an explosion into space, it was the rapid stretching of space itself. Every tiny region was blown up to a colossal size, and that process took whatever microscopic irregularities existed, the quantum jitters from the vacuum, and stretched them. Stretched them to astronomical scales. Those stretched quantum wrinkles became the seeds, the gravitational blueprints for everything to come. They dictated where galaxies would form billions of years later, and where vast voids would remain empty. Inflation also explains why the geometry of our universe appears flat. Inflating a balloon makes its surface appear flatter from any local point of view. Inflating the universe smoothed out any initial curvature. We can't see the inflaton field directly, but we see its signature. Its predictions are etched into the oldest light. The cosmic microwave background radiation, this afterglow from the Big Bang, isn't perfectly smooth. It has faint patterns, specific patterns of hot and cold spots. Missions like the Planck satellite mapped these patterns. The statistics of those spots, their size, their distribution, match the predictions of inflation. With stunning precision, it's a fossil record, a record of the universe's violent, exponential birth. So this seemingly magical event, this faster-than-light expansion of space itself, isn't a break from physics. It is physics, a consequence of applying the equations, general relativity and quantum theory in the most extreme environment possible. It set the initial conditions for everything that followed. And it left behind a whisper, a cold, uniform glow that still fills every cubic inch of the sky. That uniform glow is a fossil, a snapshot of the universe when it was an infant. It's called the cosmic microwave background. It fills every direction, a faint, cold radiation bathing everything, just 2.7 degrees above absolute zero. You can see it as static on an old television. That snowy hiss, part of it is this ancient light. It seems like a ghost, an echo from a time that's gone. But it's a direct prediction, the evidence for the hot Big Bang model. the smoking gun. Physics tells us that in the beginning, everything was a searing plasma. Thick and opaque, a soup of particles and light. Photons couldn't travel freely. They were constantly bouncing off free electrons, but the universe expanded and cooled. And then a moment, about 380,000 years after the beginning, the temperature dropped enough, protons and electrons could finally combine. They formed the first stable atoms, neutral hydrogen atoms, and in that instant the fog cleared. The photons were set free, no longer constantly scattering. They began a journey across an expanding cosmos. That first flash of transparent light is what we detect now, but space itself has expanded over billions of years. It stretched those photons, their wavelengths were pulled, redshifted, from visible heat down into the microwave part of the spectrum. That's why it's cold now. The light didn't lose energy in the traditional sense. The space through which it traveled grew. It diluted the energy, cooled it to a whisper, and this matches the equations. General relativity and thermodynamics. The universe cools as it expands. We can measure that cooling with precision. Satellites have mapped this radiation. The Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, the Planck mission. They mapped it across the entire sky, and they found it is almost perfectly uniform. Just as the theory said, but not quite, embedded in that smooth glow are tiny variations, fluctuations in temperature, just 1 part in 100,000. These anisotropies, they're not flaws, they are the blueprints for everything. They are the imprint of those primordial density wrinkles. The ones stretched by inflation, slightly denser regions, seen as slightly warmer spots in the microwave sky. They held the gravitational seeds. Over eons, gravity amplified these spots. They pulled in more matter. They grew into the first stars, the first galaxies, the vast cosmic web we're in now. By reading these patterns, cosmologists can deduce things. The universe's age, its geometry, its composition. The CMB tells us the cosmos is flat. It is 13.8 billion years old, and ordinary matter, the stuff of stars and planets, makes up only about 5% of everything. The rest is dark matter and dark energy, so this faint, cold echo, it's more than a relic, it's a foundational text, a message from the universe's first moments. Written in the language of temperature and light, it confirms the distant past obeys the laws of physics we know today. And if this echo tells us most of the universe is made of things we cannot see, then what are those shadowy components? What force is written into that ancient light, guiding everything? Galaxies are held together by a ghost. You see the stars, the gas, the light. But if you add up all that mass, it doesn't work. The stars on the outside are moving too fast, way too fast. The laws of gravity say their speed should drop off the farther out you go, like planets around the sun. But it doesn't drop, they orbit at this constant, high speed. There isn't enough visible stuff to hold them. The galaxy should fly apart, but it doesn't. Something else is there, providing the gravity. That's the signature of dark matter. It doesn't interact with light. It doesn't emit light or absorb it or reflect it. We can't see it. It's completely transparent, but it has mass, so it pulls. We detect it by seeing its effect on the things we can see. This isn't breaking the rules. It's using them. The same physics that describes a falling apple or orbiting planets tells us motion requires mass. When the mass you see isn't enough, you infer the mass you can't see. The evidence is everywhere. Look at galaxy clusters. Those galaxies are moving so fast, the visible mass of the cluster couldn't possibly hold them. There has to be this huge halo of unseen mass binding it all. We can see that mass indirectly through gravitational lensing. The dark matter warps space, bending light from galaxies behind it. It creates these arcs, these rings. By mapping that bent light, you can chart the dark matter. It's a shadow map. And then there's the cosmic microwave background, the universe's first light. The pattern of hot and cold spots tells us how much total matter exists. The amount needed is about 5 times more than all the ordinary atoms we know. The structure of the universe on every scale needs this dark scaffolding. So what is it? The physics suggests something exotic, not the stuff we're made of. It has to be a new kind of particle, something that only feels gravity and maybe the weak force. They're called WIMP, or maybe something like actions, these very light particles. These aren't just guesses, they come out of other theories in particle physics. There are experiments deep underground trying to catch one of these particles. A direct detection, so far nothing. What it is exactly is still a mystery, but that it's there isn't. It makes up about 27% of the universe. It's the invisible framework. Without its gravity to pull in the first gas clouds, galaxies might never have formed. We are here because of it. And if most of the matter is this dark, unseen thing, it points to something even stranger. That most of the universe's energy isn't matter at all. Dark matter pulls things together, it gathers, but there's also something pushing. On the largest scales, the universe isn't just expanding, it's accelerating. The galaxies are moving apart faster and faster, driven by something we can't see, dark energy. It makes up about 68% of everything, a dominant repulsive pressure woven into space itself. It seems to directly oppose gravity, a cosmic tug of war where the pull of all matter is losing to this invisible push. But that's not a contradiction. It's in the equations. Albert Einstein's theory of general relativity has a term, the cosmological constant. He put it there as a fudge factor to keep the universe static, which he thought it was. When Edwin Hubble showed the universe was actually expanding, Einstein called it his greatest blunder, but the blunder wasn't the idea, it was getting rid of it. Because that constant represents a property of empty space, a constant energy density of the vacuum. Even if you take away all matter and radiation, space itself can have a baseline energy. And in general relativity, energy curves spacetime. This particular energy creates a repulsive curvature, a kind of anti-gravity that makes the universe's expansion speed up. The physics depends on a strange quality, negative pressure. Think of a stretched rubber band. It has positive pressure. It wants to snap back to contract. Dark energy is like a rubber band with negative pressure. It wants to stretch even more. As the universe expands, more space is created. And if dark energy is a property of space, then more space means more of this repulsive energy. The push gets stronger as the cosmos grows, leading to that runaway acceleration. We didn't just theorize this, we saw it. In the late 90s, 2 teams of astronomers were watching distant supernovae. These exploding stars act as standard candles. Their known brightness lets us measure cosmic distances very precisely. The teams, the Supernova Cosmology Project and the High Z Supernova Search, expected to see the expansion slowing down. Braked by the gravity of all matter, instead they found the supernova were fainter than expected. They were farther away, the expansion was speeding up. The discovery was so shocking it earned the leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize. Dark energy was real, its effects were measurable. Today, its presence is confirmed by multiple lines of evidence. The cosmic microwave background, the large-scale distribution of galaxies, they all point to the same composition. A universe of about 5% ordinary matter, 27% dark matter, and 68% dark energy. What dark energy actually is remains one of the biggest mysteries. Is it truly Einstein's cosmological constant, a fixed property of the vacuum? Or is it something dynamic, a field that changes over time, what physicists call quintessence? Could it be a sign that our theory of gravity needs modification on the largest scales? We don't know yet, but the key point is this: the accelerating universe doesn't break known physics. It came out of it. The equations contain the possibility all along. We just had to look deeply enough into the cosmos to see it happening. This force decides the ultimate fate of everything. A future where galaxies beyond our local group will eventually accelerate away, their light fading forever from view. It's a lonely, stretching destiny written by a shadow in the equations. That lonely destiny is shaped by engines of staggering power. At the center of many galaxies, ours included, there's a supermassive black hole, but in some galaxies that black hole isn't dormant. It's feeding. We call that an active galactic nucleus. It can outshine every star in its galaxy put together for billions of years. The most extreme versions are quasars. Points of light so bright we think they're nearby stars until we measure the distance and realize we're looking back to the universe's youth. The energy output seems impossible. But it comes from a simple, violent conversion, gravity. Picture a whirlpool of gas and dust spiraling down toward the event horizon. That's the accretion disk. As material falls in, it doesn't go quietly. Particles rub together. Friction heats the disk to millions of degrees. It glows, emitting ultraviolet and X-ray light. But the process gets even more efficient. Some of the infalling material doesn't cross the horizon. Intense magnetic fields, twisted by the disk's rotation, channel a fraction of the gas. They funnel it into narrow beams, shooting it away from the poles at nearly light speed. These are the relativistic jets. If one of those jets is pointed right at Earth, we call that object a blazar. Its light can vary dramatically in hours, a sign of the incredible energies at work. All that luminosity, the glowing disk, the brilliant jets, it's not magic. It's the conversion of gravitational potential energy into radiation and kinetic energy. As matter falls deeper into the black hole's grip, it loses potential energy. That lost energy has to go somewhere. It becomes heat, light, and the furious motion of the jets. It's a titanic demonstration of Einstein's equivalence. Mass is energy. Here, mass is being converted into light on an industrial scale. The physics governing this involves general relativity, thermodynamics, and magnetohydrodynamics, how magnetic fields interact with hot, charged fluids. Supercomputers simulate these chaotic flows, and their predictions match what we see. We observe these engines across the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength reveals a different part of the story: the cool outer disk, the hot inner region, the shock waves in the jets. These aren't just distant fireworks. Active galactic nuclei are cosmic regulators. Their intense radiation and powerful jets can heat surrounding gas, preventing it from cooling and forming new stars. They can shut down a galaxy's growth, and the jets can also trigger star formation by compressing gas clouds as they slam into them. The furious nuclear reactions in the accretion disk forge heavy elements, scattering them into intergalactic space. The existence of these monsters, operating for billions of years, shows how the universe channels unimaginable forces through known physical laws. From the chaos of a feeding black hole emerges a brilliant, structured beacon, governing the life cycle of the galaxy it inhabits. And if that violence can birth and shape galaxies, where does the gentle, opposite process begin? Where does the universe gather the quiet material to build a star? From that furious galactic core, you move to a place of deep quiet, a cosmic nursery. Drifting in the spiral arms are these vast, cold clouds, molecular clouds. Dark and diffuse, light years across, just a few tens of degrees above absolute zero. Inside them, gravity does its slow work. It seems impossible that something so tenuous, so cold, could become a star. But it does. There's a rule for that, the gene's instability. If a part of the cloud has enough mass, enough density, its own gravity overcomes the internal pressure. The thermal motion of the gas that's trying to hold it up. When gravity wins, that region starts to fall inward. It's a tipping point written in the equations. The collapse isn't a straight fall because the cloud has a little rotation inherited from the galaxy. As it contracts, that spin amplifies, conservation of angular momentum. Like a skater pulling in their arms, the cloud flattens into a swirling disk, a protoplanetary disk. The center gets hot and dense, a protostar. The disk is where planets will be. But there's another force, magnetic fields threaded through the cloud. They act like brakes. They slow the collapse by tying ionized gas to the field lines. For gravity to finish, the gas has to slip past these magnetic barriers. Ambipolar diffusion. That's why it takes millions of years, not a sudden crunch. We can see this, the Orion Nebula, a stellar nursery, 1,500 light-years away. Hubble has looked into its heart, shows dusty cocoons, droplets where infant stars are being born. Their disks are silhouetted against the glow, and you see the feedback loop. The first massive stars to ignite flood the cloud with ultraviolet radiation. With stellar winds, that radiation can erode nearby clouds, stop star formation, but it can also compress other parts, trigger a new round of collapse. It's self-regulating, cyclical. The physics is classical, but it gives you incredible diversity. The initial mass of the cloud fragment decides everything. A small knot becomes a red dwarf, burns for trillions of years. A larger one becomes a star like our sun. A truly massive fragment becomes a blue giant. Short, explosive life. Every star you see, from the faintest to the brightest, started this same cold, dark way, mathematically predictable. Its birth sets the clock for its death. And in that death, it scatters new elements, forged in its core, back into space. Those heavy atoms will eventually find new molecular clouds, new disks. New planets. That quiet collapse in a dark cloud is the first, gentle step in a cycle that builds worlds and the chemistry for life. That quiet collapse gives birth to a star. It burns steadily for millions of years or billions, but every star has a destiny, and it's written in its mass. For the most massive ones, that destiny ends in a spectacle. Unimaginable power, a supernova. In a moment, a single star can release as much light as 100 billion suns. It can outshine its entire galaxy. It seems like pure cosmic violence. A final, destructive scream, but it's not an end. It's a transformation, a necessary step predicted in the life cycle of matter. It's the universe's primary forge. For the elements of life, the story begins in the star's core. For its whole life, nuclear fusion has been a balancing act. Gravity pulls in, the heat from fusion pushes out. In a massive star, this forge creates heavier elements, from hydrogen to helium to carbon, oxygen, all the way up to iron. But iron is different. Fusing iron doesn't release energy. It consumes it, so when the core finally becomes solid iron, the engine sputters and stops. The balance shatters. Gravity, unopposed, takes over. In less than a second, the core collapses. From the size of Earth down to a sphere just a few miles across, the density becomes so extreme that protons and electrons are crushed together. They form neutrons and release a flood of ghostly particles. Neutrinos. This is where the magic of physics turns collapse into explosion. For a moment, the core becomes an incredibly dense neutron star. The collapse halts, then rebounds. A shock wave forms and races outward, but on its own, that shock would stall. It would fizzle. Here's the crucial part. That flood of neutrinos carries away 99% of the star's energy. They don't all escape immediately. Some are absorbed by the material just outside the collapsing core. This neutrino heating reignites the stalled shock. It's like pouring rocket fuel on a dying fire. The shock wave is revived. It blasts outward with renewed fury, tearing through the star's outer layers at tens of millions of miles per hour. The star is ripped apart. In that incredible heat and pressure, a frenzy of nuclear reactions occurs. Elements heavier than iron, like silver, gold, platinum, are forged in seconds. Through rapid neutron capture, the star scatters its enriched guts across light years of space. We've seen this physics in action. In 1987, a star exploded in a nearby galaxy. The Large Magellanic Cloud, supernova 1987A. It was the closest supernova in centuries, and for the first time, detectors on Earth caught the neutrinos from the collapsing core. 25 neutrinos arriving hours before the light, exactly as the models predicted. The light from the explosion followed a curve. It matched our understanding of radioactive decay from the newly forged elements. It was a textbook case written across the sky. That scattered debris is the source of everything. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the hearts of stars and scattered by these explosions. The gold in a ring, the uranium in the Earth, were born in the final moments of a dying giant. This enriched gas drifts through space. It mixes with primordial hydrogen and helium. And eventually, gravity pulls it into new molecular clouds. The cycle begins again. New stars form from the ashes of the old. New planets condense, now rich with the elements for rocks, oceans, and potentially life. So a supernova is not a death. It's a necessary dispersal. A creative act mandated by the laws of nuclear physics and gravity. It shows that the cosmos operates on a principle of rebirth. The end of one story provides the raw materials for the next, and from that scattered stardust, under the right conditions, more complex structures can emerge. That stardust glows again. Not every star dies in an explosion. For one like our Sun, it's more graceful, more beautiful. It turns into a planetary nebula. A flower of light in the dark, but just for a moment. The ring nebula is the classic shape, a perfect smoke ring of gas hanging there. It looks like art. But that beauty is just physics, a sequence of events following the laws. It starts when a sun-like star runs out of hydrogen in its core. It swells into a red giant. The outer layers get cool and thin. Inside, helium starts to fuse. That phase is unstable. The star pulsates, and it begins to shed that outer envelope, not in one blast, but in a series of gentle winds. Those winds carry the star's atmosphere out into space. They form a huge, expanding shell of gas. Then the hot core is exposed. It's not fusing anymore. It collapses under its own gravity down to an Earth-sized ember, a white dwarf. This tiny, dense thing is blazing hot, over 100,000 degrees. And it floods that surrounding cloud with ultraviolet radiation. That radiation ionizes the gas. It strips electrons from atoms, and when the electrons recombine, they release light. Specific colors: oxygen glows green, hydrogen glows a deep red, nitrogen adds some blue. It's a cosmic neon sign powered by the ultraviolet light of the dead star. But the shapes, why rings or hourglasses or those intricate bubbles? The answer is in the dynamics of those earlier stellar winds. They aren't always symmetrical. The star might have a magnetic field or a binary companion, something that focuses the outflow into jets. These faster winds later catch up to the slower, earlier ejector. Where they collide, shock fronts form. They sculpt the gas. The interplay of radiation pressure from the white dwarf and these hydrodynamic shocks creates the forms we see. The Helix Nebula looks like a giant eye. The Cat's Eye Nebula has these complex knots and jets. Each shape is a fossil record, the star's final breaths. And this phase is incredibly brief, just tens of thousands of years. In the billion-year life of a star, it's a blink. The glowing gas disperses into the interstellar medium. It enriches it with new elements, carbon, nitrogen. The white dwarf remains, a dense sphere of degenerate matter, where electrons are packed so tight they provide a quantum pressure. That supports the star against more collapse. It will cool slowly over billions of years, fading to a black dwarf, so the planetary nebula is the transition. That beautiful, fleeting marker between a star's life and its long, quiet afterlife, it shows that even in death there's structure, there's light, a return of materials to the galactic cycle. And that white dwarf, if it has a companion, can set the stage for a different kind of resurrection, one that breaks the sky with predictable light. That white dwarf isn't just a fading ember. It's a new state of matter, a star held up by a quantum force. When a star like our Sun dies, it sheds its outer layers. What's left is the hot, dense core. That core collapses under gravity, but the collapse stops. It stops at about the size of Earth, yet it holds nearly the entire mass of the Sun. A teaspoon of it would weigh tons. That's the white dwarf, and what holds it up isn't fusion heat. It's a quantum rule, electron degeneracy pressure, the Pauli exclusion principle. No two electrons can be in the same quantum state. Gravity squeezes the star, forcing electrons closer, but they resist. They can't all be forced into the lowest state. That resistance creates an outward pressure. It's not about temperature or motion. It's a quantum mechanical pushback. The star is supported by the stubbornness of particles. This gives white dwarfs a strange property. The more massive they are, the smaller they get. Add mass, and gravity squeezes it denser. But this defiance has a limit. Subramanian Chandrasekhar calculated it. If a white dwarf's mass exceeds about 1.4 solar masses, the pressure fails. Gravity wins. The star collapses further into a neutron star or a black hole. That's the Chandrasekhar limit. It tells us which stars become these dense embers and which meet more violent ends. We've confirmed this by observing white dwarfs nearby. The most famous is Sirius B, the faint companion to Sirius. It has a mass like our Sun, but it's only slightly larger than Earth. Its intense gravity was inferred from its effect on Sirius A, long before we saw it directly. We also use white dwarfs as cosmic clocks. They have no energy source, they just radiate leftover heat. By measuring temperature and brightness, we plot a cooling curve. The faintest, coolest white dwarfs in a cluster tell us how old that cluster is. It's a way to date stellar populations. Their destiny is to cool and fade over tens of billions of years. To become cold, dark spheres of crystallized carbon and oxygen, black dwarfs. The universe is 13.8 billion years old. It's not yet old enough for any black dwarf to have formed. Every white dwarf we see is still glowing with residual heat. These objects are a demonstration. They show how the rules of the very small, the quantum rules, dictate the fate of the very large. They create a stable, bizarre endpoint for stars like our own. And when such a star has a companion, this quantum-supported cinder can become a trigger. For one of the universe's most predictable explosions, the white dwarf has this extreme cousin, the neutron star, that city-sized atomic nucleus it can spin. And when it spins, it becomes a beacon, a cosmic lighthouse. Its rhythm is so precise it rivals our best atomic clocks. These are pulsars. They were first detected not as light but as a pattern. A regular, repeating pulse in radio telescope data. Jocelyn Bell Burnell noticed it. She was a graduate student then, in 1967. The signal was so unnervingly regular they nicknamed it LGM. Little green men, but the truth was more fascinating. It was natural, known physics pushed to an extreme. When a massive star collapses into a neutron star, it conserves its angular momentum. Like an ice skater pulling in their arms, the star's slow rotation becomes a frantic spin. A newborn neutron star can rotate hundreds of times per second. But it isn't just spinning matter. It has a magnetic field, inherited from its parent star, amplified by the collapse to unimaginable intensity, trillions of times stronger than Earth. Charged particles, electrons, protons, get caught near the magnetic poles. They're accelerated to near light speed along the field lines. As they spiral, they emit a tight beam of radiation. usually radio waves shooting out from each magnetic pole, and the magnetic axis is tilted. It isn't aligned with the rotation axis, so as the star spins, those beams sweep through space. Like a lighthouse beam, if Earth lies in the path, we see a flash with every rotation. A pulse, that's a pulsar. The incredible regularity comes from the rotational inertia of a star more massive than our Sun, compressed into a sphere just a dozen miles across. Nothing in everyday life can slow it down quickly. It's a flywheel of staggering mass and density, and we use them because of that precision, they're tools. In a binary system with another neutron star, the pulses act as a probe. The orbit causes tiny, predictable delays and advances in the pulse timing as the pulsar moves through the curved spacetime of its companion. By tracking these shifts, astronomers confirmed predictions of general relativity with exquisite accuracy, including the emission of gravitational waves that slowly drain orbital energy. That work earned Russell Hulse and Joseph Taylor the Nobel Prize in 1993. It was an indirect detection of Einstein's ripples in spacetime. Decades before LIGO direct observation, some pulsars get a second life. If a neutron star has a companion star, it can pull material from it. This falling gas transfers angular momentum. It spins the pulsar up to dizzying speeds. These are millisecond pulsars rotating hundreds of times per second. They become even more precise clocks. Used in experiments to detect low-frequency gravitational waves from supermassive black hole mergers across the cosmos. So these cosmic lighthouses, born from stellar catastrophe, are not chaotic. They are paragons of order. They show how conservation and electromagnetism, under the most severe conditions, produce a signal so clean we can use it to test the fabric of reality itself. From their precise ticks, we learn to listen for the whispers of spacetime. The heartbeat of a dead star, that's one rhythm, but the universe has another rhythm, a slower one. A dance of giants, not two stars, but two entire cities of stars, galaxy clusters. Each one holds hundreds of galaxies, all bound by gravity, swimming in dark matter and superheated gas. When two of these structures meet, it's the largest collision in the universe. They don't crash, they pass through each other, a ghostly intermingling over billions of years. It should be pure chaos, an impossible tangle, yet these mergers, like the bullet cluster, give us one of the clearest proofs for dark matter. Here's how. In a cluster merger, the different parts behave in distinct ways. The galaxies themselves are mostly empty space. They slip past one another like swarms of bees, barely interacting. The hot gas between the galaxies is different. That thin, multimillion-degree plasma is governed by electromagnetic forces. As the clusters collide, this gas smashes together. It creates immense shock waves. It slows down, piles up, gets left in the middle. We see this gas with X-ray telescopes like Chandra as a bright, glowing cloud. But most of the mass isn't in the galaxies or the gas. It's in the dark matter, and dark matter doesn't feel the electromagnetic force. It only responds to gravity. So when two dark matter halos collide, they pass right through. They keep going ahead of the lagging gas. This creates a separation. The gravitational mass, mapped by how it bends light, gravitational lensing is in one place. The visible, glowing X-ray gas is in another. The bullet cluster shows this. The pink clouds of hot gas are stuck between the two clusters. The blue contours of mass, the dark matter, have sailed ahead with the galaxies. It's a cosmic fingerprint. The mass is not where the light is. That offset is direct evidence that most of the matter is something invisible, something that only interacts via gravity. The energy released is staggering. It heats gas to even more extreme temperatures. It can accelerate particles to near light speed, creating vast, diffuse radio emissions called radio halos. These are the scars of the collision, visible across the electromagnetic spectrum. and we can simulate it. Using supercomputers, physicists model these events with gravity and hydrodynamics. The simulations produce the same separated features, the same shock structures, the same radio halos we observe. They show how the largest structures form and evolve through a slow-motion ballet of attraction and collision. These cosmic collisions show that even on the grandest scales, the driver is simple, relentless gravity. It pulls clusters together over eons, orchestrating mergers that reshape the cosmic web. And in that violence, space-time is not a passive stage. It is stirred, sending out whispers that travel at the speed of light. The whispers of space-time are real. We can hear them now, two black holes, each tens of times the mass of our sun. They spiral together in a final dance. They don't just vanish, they shake the universe. Their masses are immense, accelerating, and they send out ripples in the fabric of space-time itself. Those are gravitational waves. They stretch and compress everything they pass through. But the amount is almost impossibly tiny. For a wave from a distant merger, the distortion could be smaller than the width of an atomic nucleus, over a distance of 4 kilometers. Detecting that faint tremor feels like magic, but it's a direct prediction from Einstein's theory of general relativity, written over a century ago. The physics is specific. A mass sitting still or moving at constant velocity doesn't produce these waves. You need acceleration, and not just any acceleration. You need a changing quadrupole moment. That's a term for a particular kind of asymmetric motion. Think of two black holes orbiting. As they whip around, the distribution of their mass in space is constantly changing. In a lopsided way, this accelerating, asymmetric mass generates the waves. They travel outward at the speed of light, carrying energy away. That energy loss causes the orbits to decay. It forces the black holes to spiral inward faster and faster until they finally merge. The waveform, the specific pattern of the ripple in time, is a precise prediction. It's like a cosmic fingerprint. For decades, these waves were theoretical. Then, in September 2015, LIGO made the first direct detection, the Laser Interferometer Gravitational Wave Observatory. The signal matched the waveform of two black holes merging, about 30 solar masses each, over 1 billion light-years away. It was a triumph, a validation of Einstein in the most extreme regime. Since then, LIGO and Virgo have heard dozens of these cosmic tremors, not just from black holes, from neutron stars colliding. That event in August 2017 was a landmark. The gravitational wave signal arrived, followed 2 seconds later by a flash of gamma rays, then a glow across the electromagnetic spectrum. It was multi-messenger astronomy. The waves told us what happened and where. The light told us what it was made of. It revealed the forge where heavy elements were created, gold and platinum. This new sense changes everything. Light can be blocked or scattered. Gravitational waves pass through almost anything. They let us probe the dark universe. To census populations of black holes we could never see. To test gravity in its strongest possible field. To potentially listen to the vibrations of a newborn neutron star. And learn about the mysterious state of matter in its core. Each detection is a direct message from a warped region of space-time, obeying equations we derived on Earth. It confirms the stage of the cosmos is not static. It's a dynamic, elastic entity, ringing like a bell with every cataclysm. And if we can hear the ringing of space-time, what other textures of reality might we learn to perceive? The ringing tells us something's there, something inside that star. We go past the surface, into the heart of it. The conditions there, they're beyond anything we can make here. The pressure is just immense. It crushes atoms. Electrons get pushed into protons. Everything turns into neutrons. That's nuclear density. A sugar cube of that material would weigh 1 billion tons. It sounds like fantasy, but the properties are there, in the equations, and it's not just a uniform soup, it's layered, like an onion. The outer crust is rigid. A lattice of atomic nuclei, mostly iron, sitting in a fluid of electrons, but you go deeper. The nuclei get squeezed until they touch, and then they dissolve. You're in the inner crust then, a mix of neutron-rich nuclei and free neutrons that have dripped out. Go further, the core. Here we leave familiar physics. Where in theory, the neutrons under that pressure, they might break down themselves. Their quarks could come free. A soup of quark-gluon plasma, or maybe exotic particles form. Hyperions, neutrons with strange quarks. This is the domain of the strong force, the strongest glue, tested to its limit. We can't go there, so we listen. The stars themselves, a pulsar's spin clock perfect, will sometimes speed up just a tiny jump, a glitch. The leading idea is a starquake. The solid crust, under strain from the slowing superfluid inside, it cracks. It shifts like tectonic plates, but on a surface harder than diamond. That releases energy, tweaks the rotation. Those tremors from a place of impossible density, they telegraph the structure. To our telescopes, we also learn by weighing, measuring. X-ray observatories, like NICER on the space station, they do cosmic cartography, map the hot spots on the surface. Measure how the gravity bends the X-ray light. From that, scientists get the star's mass and its radius. That data point, mass versus radius, it's a fingerprint. It rules out whole families of theories about the interior. Is the core soft, stiff? Are there free quarks, exotic particles? Each possible equation of state predicts a different curve. And the stars tell us which curves are real. The implications go from the cosmos to the quantum. Conditions in the core might allow proton superconductivity, neutron superfluidity, particles flowing without friction. These quantum behaviors on a stellar scale could explain the origin of the star's colossal magnetic field. Studying these interiors is a grand experiment, using the universe as the lab. It forces us to bridge the world of subatomic particles with gravity, with relativity. And the strange matter hypothesized inside, it might even be stable on its own, which leads to a possibility, a tantalizing one, that some neutron stars could be seeds for something even stranger, a form of matter so fundamental it redefines what a star can be. That strange matter might not stay contained. There's a theoretical boundary, a hypothetical star made entirely of it. A strange star, it would be the densest stable object possible, not held by gravity but by something more fundamental, the strong nuclear force itself. In a neutron star, the neutrons are packed so tightly they're almost touching. But in a strange star, they break down. The pressure overcomes the force binding quarks inside neutrons. The neutrons dissolve, their quarks up quarks and down quarks spill out, and they can transform. Through the weak nuclear force, some down quarks change into a different flavor. The strange quark, you get a soup of free quarks, up, down, and strange, swimming in a sea of gluons, the particles that carry the strong force. That's quark matter. And according to quantum chromodynamics, our theory of the strong interaction, this quark-gluon plasma could be the true ground state of matter at these densities. More stable than the nuclear matter in a neutron star. It's a radical idea. It suggests that under enough pressure, the universe prefers its building blocks unconfined. We can't create these pressures on Earth, not for a stable object, but particle colliders like the Large Hadron Collider can create fleeting micro-fireballs of quark-gluon plasma, recreating conditions a microsecond after the Big Bang. That tells us the state exists. The question is whether nature can squeeze matter enough and keep it squeezed to form a permanent quark star. If they exist, strange stars would look deceptively like neutron stars from a distance. Pulsing, dense, and small, but the details would give them away. Their mass-radius relationship would be different. a strange star could be smaller and heavier than a neutron star of the same mass. Or it could have a much lower maximum mass. Some observed pulsars, like Pulsar J0030 plus 0451, have masses and radii that are hard to explain with standard neutron star models. They sit in a puzzling region of the mass-radius diagram. Could they be strange stars? We don't know. Their surfaces would be different too. Instead of a solid iron crust, a strange star might have a crust of normal matter, floating on top of the quark sea like a thin layer of ice on an ocean. Or it might have no crust at all, presenting an impossibly smooth surface. The implications are profound. A strange star's core wouldn't have the layered structure of a neutron star. It might be a single, uniform fluid all the way to the center. This could affect how it spins, how it cools, and how it rings when disturbed. A starquake on a strange star would propagate through quark matter, not nuclear matter, potentially leaving a different seismic signature in its pulse timing. This is the cutting edge where astrophysics meets particle physics directly. We use telescopes to probe conditions so extreme they test the very theory of how matter is built. The search for strange stars isn't just about finding a new class of object. It's about asking if, under the most intense pressures the cosmos can muster, the rules change. If quarks decide they are better off free, it pushes our understanding of stability to the limit, and it reminds us that the universe may harbor forms of matter we have only dreamed of in equations. From this hypothetical pinnacle of density, we shift our gaze to the opposite extreme, the vast, echoing emptiness between the galaxies. That hypothetical peak of density is surrounded by almost nothing. Between the great walls and filaments, you have the voids, these immense spherical regions of near emptiness. They stretch for hundreds of millions of light years. In some, you could travel for a lifetime and never find a single major galaxy. It feels like a cosmic oversight, a place where the universe just forgot to put anything. But these voids aren't accidents. They're a fundamental part of the structure, predicted, born from the same physics that built the clusters. It starts with the faintest whispers in the early universe. Those quantum fluctuations from inflation imprinted on the cosmic microwave background, those were the seeds, slightly denser regions and slightly less dense ones. Over billions of years, gravity acted as an amplifier. It pulled matter from the less dense regions, the underdensities, toward the overdensities, like water draining from a bathtub. The underdensities expanded, becoming emptier. The overdensities condensed into the great clusters and filaments. The voids are the drained basins. Their growth is a direct result of gravitational instability. And the expansion of the universe itself, this process is sculpted by the unseen components. Dark matter forms the gravitational skeleton. Its pull guides the flow. Then dark energy, acting as a repulsive force on cosmic scales, accelerates the expansion. And because voids are already underdense, with less gravitational pull holding them back, they expand even faster than the average Hubble flow. They're regions where dark energy's influence is most pronounced, stretching the emptiness wider. Far from being barren deserts, voids are laboratories. Their size, shape, distribution, they're sensitive to the laws of cosmology. By mapping thousands of them, astronomers can test theories of gravity. Does gravity behave the same in these vast, empty realms as it does in the crowded clusters? The answer so far is yes. General relativity holds even here. Studying the rate at which voids grow also gives us a measure of dark energy's strength. It's a different kind of test, complementary to supernova, a unique window into the force that dominates our universe's fate, and they're not completely empty. They contain a sparse population of isolated dwarf galaxies, drifting like lonely ships. They hold vast amounts of extremely thin million-degree gas. So diffuse it's almost a perfect vacuum. Even this tenuous material obeys the same thermodynamics as gas in a cluster, just at an impossibly quiet volume. The galaxies that do form in voids are often different, quieter, less disturbed, pristine examples of galactic evolution in isolation. These vast expanses of nothing are a humbling reminder. For all the brilliance of stars and the fury of black holes, the universe is overwhelmingly empty space. The glittering structures we cherish are the rare exceptions. The dense knots in a grand, mostly vacant tapestry. The same physical principles govern both the crowded city and the desolate plain. From the echoing quiet of a void, we turn to the opposite. To particles that never stop moving, that fill every inch of that emptiness with an invisible, energetic rain. There's an invisible rain falling on us all the time. Particles from deep space moving almost at light speed, hitting the atmosphere. They're called cosmic rays, not light atomic nuclei, mostly protons stripped of electrons, accelerated to incredible energies. They come from across the galaxy and beyond, a constant, silent bombardment. It seems impossibly violent, but their existence, their speed, isn't a mystery. It's a direct consequence of known physics. The universe becomes a natural particle accelerator on an unimaginable scale. The question is how? How does a simple proton get that much energy, enough to cross cosmic distances at such a staggering fraction of light speed? The answer is acceleration, a process that happens in the most turbulent places in the cosmos. One of the main engines is a supernova remnant shock wave. Picture the expanding shell of debris from a stellar explosion, plowing through space at millions of miles an hour. That creates a colossal shock front. Charged particles, like protons, get trapped in the turbulent magnetic fields near that shock. They bounce back and forth, crossing the shock boundary again and again. Each time they cross, the moving magnetic fields transfer a little more energy to them. It's a natural particle accelerator, a process first theorized by Enrico Fermi. Over time, these particles gain tremendous energy, and eventually they break free. They travel across the galaxy, but supernovae aren't the only accelerators. There are also the relativistic jets from active galactic nuclei, powered by supermassive black holes. Those are even more powerful. Their intense magnetic fields and extreme velocities can propel particles to energies far beyond what any supernova remnant can achieve. These are likely the source of the ultra-high-energy cosmic rays, the most energetic particles ever observed. A single one of these rare particles carries the kinetic energy of a well-thrown baseball, all packed into a single subatomic nucleus. The physics to explain it involves special relativity, complex magnetohydrodynamics, but the principle is the same. Electromagnetic fields over vast distances and times gradually pump energy into a charged particle. We detect these particles not by catching them directly, but by observing the aftermath. When an ultra-high-energy cosmic ray strikes a nucleus in our upper atmosphere, it triggers a cascade. A shower of secondary particles, muons, electrons, photons rains down over several square miles. Giant observatories like the Pierre Auger Observatory in Argentina use arrays of detectors to map these air showers. By studying the pattern, the particles within it, scientists can work backwards. They can estimate the original cosmic ray's energy and, to some degree, its direction. And this is where a puzzle emerges. The highest energy cosmic rays should point back to their sources. But they don't, not clearly. The reason is the galaxy's magnetic field. It's weak, but it's everywhere, weaving through interstellar space. These fields act as a cosmic maze, bending the paths of charged particles. A proton arriving from a distant galaxy has been deflected, scrambled so many times over its million-year journey that its original direction is lost. It's like trying to trace the path of a pinball by where it finally lands. so we understand the acceleration mechanisms, but pinpointing the exact accelerators for the most energetic rays remains an active hunt. This invisible rain is more than a curiosity, it's a probe. By studying how cosmic rays are distributed, how they interact, we map the magnetic fields of our galaxy. We test our models of particle physics at energies unreachable in human-built colliders, and we're reminded that the empty space between stars isn't truly empty. It's threaded with magnetic fields crisscrossed by these relentless, high-speed travelers, all governed by the elegant, relentless laws of electromagnetism and motion. That invisible maze of magnetic fields isn't just a tangle, it's a web, a structured web that threads through the whole galaxy. These galactic fields are faint, but they're everywhere. They shape how gas flows between the stars, they guide those high-speed cosmic rays scrambling their journeys, and they leave a signature in the light we see. It seems like a background whisper, this architecture, but it's a dynamic force generated and sustained by the galaxy's own motion. The engine is a dynamo. A process where the galaxy's rotational energy, through the motion of its conductive plasma, gets turned into magnetic energy. It's magnetohydrodynamics in action. The spiral arms of our Milky Way aren't just lanes of stars, they're rivers of ionized gas. This plasma is a conductor. As the galaxy rotates, this conducting fluid moves through any weak, pre-existing magnetic field. That motion, that shear, it stretches and twists the magnetic field lines. It amplifies them. It's like a self-exciting generator, but on a scale of 100,000 light-years. The seed for this could have been incredibly small. A primordial field from the early universe, maybe from phase transitions or the motions of the first plasma. That tiny seed gets wound up, amplified over billions of years by the galactic dynamo. The result is the large-scale, coherent field we detect now. But how do we see something invisible? We observe its effects on light. When high-energy electrons, often from supernova shocks, spiral around these magnetic field lines, they emit synchrotron radiation. This light is polarized. Its electric field vibrates in a preferred direction, aligned with the magnetic field. So by mapping this polarized radio emission across the sky, astronomers trace the field's structure. We see it follows the spiral arms like grooves on a record. Another tool is Faraday rotation. As polarized light from a distant quasar passes through our galaxy's magnetized plasma, the magnetic field twists the polarization angle. By measuring this rotation at different radio frequencies, we can map both the strength and the direction of the magnetic field along that line of sight. These observations show a complex tapestry, fields that are ordered on large scales but turbulent and tangled in the dense clouds where stars are born. This magnetism isn't a passive decoration, it's a key player. It provides pressure that supports giant molecular clouds against gravity's collapse, slowing down star formation. It channels the flow of gas, influencing how spiral arms maintain their structure. When a star does form, magnetic fields help carry away angular momentum, letting the protostar condense. They also collimate the powerful jets from young stellar objects, focusing them into narrow beams. On the largest scales, these same principles of magnetohydrodynamics govern the spectacular jets from active galactic nuclei, confining plasma into streams that can pierce through intergalactic space. Those cosmic rays we discussed earlier, their paths aren't random walks. They're guided by this galactic magnetic web, their trajectories sculpted by its lines of force. This invisible framework shows that electromagnetism is as fundamental as gravity in shaping the cosmos. It operates from the smallest planetary realms to the largest galactic structures, a unifying thread in the physics of the universe. And when these magnetic principles interact with a planet's atmosphere, they create one of the most visually stunning phenomena in all of nature. Those magnetic fields shape more than gas. They shape the sky, not only our sky, but skies everywhere in the solar system. Aurorae, those shimmering curtains of light at the poles, we have them on Earth, the northern and southern lights. But they're not unique to us. Jupiter has them, Saturn has them, and theirs are on a scale that dwarfs our whole planet. These light shows can seem like magic, distant and untouchable. But they are a direct result of known physics, a universal process of electromagnetism and chemistry. It starts with a stream of charged particles, the solar wind flowing from the sun. Or for Jupiter, particles from its volcanic moon, Io. These particles, electrons and protons, carry an electric charge. When they meet a planet's magnetic field, everything shifts. The field acts as a guide. It channels the particles along its lines of force. The particles spiral down toward the magnetic poles, accelerating into the upper atmosphere. And there they collide with gas atoms and molecules, oxygen, nitrogen, hydrogen. The collision transfers energy. It excites the atmospheric atoms. They jump to a higher energy state. But they can't stay there. In a tiny fraction of a second, they fall back down, and they release that extra energy as a photon, a particle of light. That's the glow. The specific color depends on the gas and the altitude. On Earth, oxygen gives greens and reds. Nitrogen gives blues and purples. On Jupiter and Saturn, where the atmosphere is mostly hydrogen, the aurorae glow in ultraviolet and a deep red. It's a celestial fingerprint. It reveals the planet's composition from millions of miles away. The power of these alien aurorae is staggering. Jupiter's magnetic field is 20,000 times stronger than Earth. Combined with the planet's 10-hour rotation, it creates a magnetosphere so vast it would appear larger than the full moon in our sky if we could see it. This system acts like a colossal particle accelerator. The Juno spacecraft, orbiting Jupiter since 2016, has flown right through these auroral currents. Its measurements show that Jupiter's aurorae aren't mainly powered by the solar wind. They're powered by the planet's own internal dynamo and material from Io. The volcanic moon spews sulfur and oxygen ions into space. They get trapped in Jupiter's magnetic grip. As the planet spins, it whips this plasma around, generating millions of volts. That drives particles crashing into the atmosphere. The resulting auroral ovals are permanent, raging rings of light. Each one is larger than Earth itself. Saturn's aurorae are equally magnificent, shaped by its unique magnetic geometry. The Cassini spacecraft saw them in detail. They pulse in rhythm with the planet's radio emissions, a heartbeat written in light. Even planets with weak or no magnetic fields, like Mars and Venus, can have diffuse auroral glows. It happens when solar particles strike their atmospheres directly. The phenomenon is universal. Wherever a charged wind meets a world with a magnetic field and a thin veil of gas, light will follow. That brings us to the end. 25 cosmic phenomena. From the crushing density of neutron stars to the silent growth of cosmic voids. From the impossible speed of superluminal jets to the gentle glow of a planetary nebula. Each one, at first glance, seems to defy logic. A teaspoon of star stuff heavier than a mountain, empty space boiling with virtual particles, a universe expanding faster and faster. But we've seen, step by step, that none of them break the rules. They are the rules. They are the inevitable consequences of applying physics, gravity, quantum mechanics, electromagnetism, thermodynamics to the cosmos. The true wonder isn't that the universe allows these impossibilities. It's that our human minds, through patience and curiosity, have crafted principles that can explain them. We've taken the chaos of the heavens and found an underlying order, an order so profound it predicts black holes and time dilation, cosmic inflation and quark matter. We've listened to the ringing of spacetime. We've mapped the magnetic fields of galaxies. We've used the cold afterglow of creation to weigh the unseen components of everything. And yet mysteries remain. We know dark matter exists by its gravity, but we don't know what it is. Dark energy drives the acceleration of the universe, but its true nature is a profound puzzle. The singularity at the heart of a black hole is a place where our equations fail. The quest to unify gravity with quantum mechanics continues. These aren't failures of physics. They're its frontiers. They're the next chapters in a story of discovery that began when the first human looked up at the stars and wondered. So the next time you see a picture of a swirling galaxy or hear about the detection of a gravitational wave, remember this. You're not looking at magic. You're looking at a universe that operates by a knowable, elegant, and often astonishingly beautiful set of rules, and we are just beginning to read them. The cosmos isn't a series of separate miracles. It's one big thing, really, just a few deep principles playing out. We've watched the impossible become real, and it wasn't magic. It was law. The math for a falling apple is the same math for a pulsar's orbit. That quantum jitter in empty space, that's what seeded the galaxies. This unity, that's the biggest discovery. It means the universe makes sense. Our trip through neutron stars, dark energy, gravitational lenses, quark matter, it all shows a consistent reality. Each extreme thing is like a cosmic lab. It tests our theories at the edge and confirms how strong they are. The flash from a gamma ray burst and the cold, uniform echo of the cosmic background radiation, they follow the same thermodynamics. The shape of a spiral galaxy and the path of a single photon bending near a black hole, they both obey Einstein's geometry. This synthesis changes how we see things. The awe we feel isn't for chaos, it's for an order of breathtaking scope and elegance. The things we still don't know, what dark matter really is, the essence of dark energy, the final theory of quantum gravity, they aren't signs that physics is broken. They're the next puzzles. They're part of a grand, ongoing investigation. They're the blank spaces on a map whose borders we've already charted with confidence. This understanding is a profound gift. It tells us that when we look up at the night sky, we aren't just looking at pretty lights, we're looking at a system. A system we can learn to read with patience and ingenuity. The universe whispers its rules in every wavelength of light, in every ripple of space-time. In the vacuum between the stars, our job is to keep listening, to keep questioning, and to keep building the story of everything from the whispers we've learned to hear. The cosmos isn't a collection of separate miracles. It's one thing, a few deep principles playing out. We've seen the impossible become real, and it wasn't magic. It was law. The math for a falling apple is the same math for a pulsar's orbit. That quantum jitter in empty space, that's what seeded the galaxies. This unity, that's the biggest discovery. It means the universe makes sense. Our trip through neutron stars, dark energy, gravitational lenses, quark matter, it all shows a consistent reality. Each extreme thing is a cosmic lab. It tests our theories at the edge and confirms how strong they are. The flash from a gamma ray burst and the cold, uniform echo of the cosmic background radiation follow the same thermodynamics. The shape of a spiral galaxy and the path of a single photon bending near a black hole, they both obey Einstein's geometry. This synthesis changes how we see things. The awe we feel isn't for chaos, it's for an order of breathtaking scope and elegance. The things we still don't know, what dark matter really is, the essence of dark energy, the final theory of quantum gravity, they aren't signs that physics is broken. They're the next puzzles, part of a grand, ongoing investigation. They're the blank spaces on a map whose borders we've already charted with confidence. This understanding is a profound gift. It tells us that when we look up at the night sky, we aren't just looking at pretty lights, we're looking at a system. A system we can learn to read with patience and ingenuity. The universe whispers its rules in every wavelength of light, in every ripple of space-time. In the vacuum between the stars, our job is to keep listening, to keep questioning, and to keep building the story of everything from the whispers we've learned to hear. The astronomer Carl Sagan once shared a thought. He said, "Somewhere, something incredible is waiting to be known. That's the heart of this journey. Every mystery we solve peels back a layer, only to reveal deeper questions beneath." That's not a frustration, it's the engine of discovery. It's what drives us forward. It means the adventure never truly ends, so let this exploration be a beginning. The next time you're under a dark sky, look up. Let that sense of wonder return, but now let it be a curious wonder. You know, each point of light, each dark patch of space, is part of a grand, logical, and beautiful narrative. A narrative written in the language of physics. If this voyage sparked your curiosity, there's more to discover. Consider subscribing for more deep dives into space and time. We'd love to hear from you. Which of these cosmic phenomena left you the most amazed? Was it the city-sized atomic nucleus of a neutron star, or the silent, stretching power of dark energy? Share your thoughts in the comments. Thank you for sharing this journey. Remember, the universe is not just stranger than we imagine, it is stranger than we can imagine. Yet, piece by piece, we are learning to imagine